Hello everyone, welcome back to my channel. So in this video we are gonna talk about work, energy, and power. So this is also IB physics part 5. Which is the last part of mechanics. IB physics mechanics. I know this is a really long chapter, but it's very important for you to have a good understanding about this unit. So follow my website. It has more practice problem because I might not have time to make all video solution for our problem. I have posts in the website, so you can go to the website to find the solution. So first of all, you're gonna talk about work. So work is a measure of energy transfer that occurs when an object is moved over a distance by external force, at least part of which is applied in the direction of the displacement. So one thing to understand about work is that work is a scalar quantity. And this is because dot product. So you might not have learned dot product now, but you probably will learn it in the future, especially if you're a physics major student. And the formula to calculate work is this, where F is the force applied. This D is displacement traveled by the object. Theta is the angle between F and D. And work has a SI unit of joule, which is equal to kilogram times meter square over second square. So let me write this. So this is the SI unit. You will see why the base unit is the following when we talk about kinetic energy. So let's talk about more about what work really is. So let's say we have an object which has a mass of m and then is moved in the direction, has a displacement of d, and I apply a force of F. So the angle between the displacement and the force will be theta, right? So work will be equal to force times displacement times cosine theta, right? So really in the integral form, because now we are talking about constant force, but force might change. Then it becomes something like this. So here, this part here might be, let's say, dr. This will be F and this will be theta. So work will be equal to integral past, let's say, AB times, F and the displacement and cosine. So this is the integral form. If the force is applied in this way, so let's say we have an upward force, right? F1, then the work will be equal to 0, because cosine 19 degree is equal to 0. Right, so let me write this down. So let's say this is mass this is F, and this is displacement. Then the angle here will be 19 degree. So work will be equal to FD cosine 19 degree, which is equal to FD times 0. So work will be equal to 0. So just be aware of the direction. Same thing if you are going upward with the displacement of D and you apply a rightward force here, work will be equal to 0 as well. So remember, the angle refers to the angle between F and D. So the angle between the force and displacement traveled by the object. So let's do a quick example. So a mass is being pulled along a level rope by a rope attached to it in such a way such that the rope make an angle of 34 degrees with the horizontal. The force applied on the rope is 24 newtons. Calculate the work done by this force in moving the mass a distance of 8 meters along the level rope. So in this problem, it doesn't matter, the direction does not matter. So distance can be seen as displacement. So here is the mass. I don't know, I'm better drawing. Let's say the angle here is 24 degrees. So what is the work done? And we know the force here will be 24 Newton. So it looks something like this. Right, so work will be equal to FD cosine theta, where theta is the angle between force and displacement. So this is equal to, the angle here is 34. 24 times A cosine 34 degrees, which is equal to 159.175 joules. So this is an approximation. So I just thrown the digit to the nearest southern place. Now let's talk about kinetic energy. So this is a type of energy, and same thing. Kinetic energy is the energy an object travels because it's motion, and this makes sense, right? Because it has the word kinetic, right? So energy E is also scalar quantity. And when an object is moving at velocity of v, it obviously has some energy. You know it because it's moving, right? So kinetic energy usually represented by the capital letter K is equal to half times mass times velocity squared. So if you want to calculate changing kinetic energy, it will be equal to Kf minus Ki, which is equal to a half time mass Bf squared minus a half Bi squared, so equal to a half Bf squared minus Vi squared, right? So some people might write it in this way. Changing kinetic energy is equal to a half m times delta v squared. Just be aware that delta v is equal to, delta v squared is equal to vf squared minus vf squared. So vf is final velocity and vi is initial velocity. Also, energy also has a SI unit of joule, right? And why we talk about the base unit? So kg times meters square over second square, and this makes sense because mass has a unit of kilogram, and velocity has a unit of meter square per second square. So this is why the SI unit, SI base unit is the following. So here should be a -2. So let's do a quick example. So it says, what is the kinetic energy of an 80-gram athlete running at 10 meters per second? So part A, we know kinetic energy is equal to a half times mass times v velocity square. So a half times 80 times 10 square. So this is equal to 40, and this is equal to 100. So this is gonna be 4,000 joules. Part B, the crater in Yucatan, I don't know, one of the greatest existing impact crater on Earth, is thought to have been created by an asteroid traveling at 22 kilograms per second and releasing 4.2 times 10 to the 23rd joules of kinetic energy at point impact. What is the mass? So from this formula, we know that mass is equal to 2 times kinetic energy over V squared. So we know the kinetic energy here is equal to 2 times 4.2 times 10 to 23rd power over so 22 kilograms per second. So you need to convert the unit. So 22 kilograms per second to meter per second. You just time 10 to the third power, right? Because 1 km is equal to 1,000 meter, and this is equal to. So let me plug this into my calculator. So this is equal to 3.82 times 10 to the positive 12th power. What's that? Unit of kilogram. Part C, in nuclear reactors, thermal neutrons traveling at a speed of 2.2 kilograms per second play an important role. What is the kinetic energy of such a particle? So for this one, same thing. K is equal to a half times V squared, which is equal to what is the mass of the. So this part, it doesn't give us mass. So let's just assume the mass is 1 kilogram for some simplicity. So it's gonna be 1 times a half times 2.2. Convert that to meter per second. So this is just gonna be equal to 1.1 times 10 to the third power. What's the unit of joule? So work energy and thermal. Work energy thermal is very simple. Basically it says this. So work done is equal to change in kinetic energy. So a half times mass times VF square minus VI square. So this is what work energy thermal state. So how do we prove this thermal? So let me do this. So work done is equal to VF square minus VS square. So let me prove this thermal. So from motion, we know the formula of VF square minus VI square is equal to 2 times acceleration times displacement. And from Newton's law, we know that F is equal to mass times acceleration. So acceleration is equal to F over m. So this now becomes something like this. 2 times F over ms. So what happened is that you divided by 2. Both sides is divided by 2. So I have VF square minus a half VI square is equal to FMS, right? Oh, sorry, here's and then you multiply both sides by m. So now something become this. And this we know is changing kinetic energy. And this is work done. Now we are gonna talk about potential energy. So potential energy is defined as mechanical energy, stored energy, or energy caused by a position. So in this lecture, we are gonna basically talk about gravitational potential energy, mg, which is mgh, the formula to calculate. And another one is spring potential energy. So spring potential energy, this is its initial position, final position, and how much energy is stored in the spring. So potential energy is stored, right? Is a something stored in something, such as spring, right? For example, stretch it here, some energy is stored in the spring. So spring energy, or you can also say elastic potential energy, is the energy stored as a result of the formation of an elastic object, such as stretching of a spring, right? So let's say here is spring, and this is initial position xi. So here is the initial position, then you start to move and go to another position in this picture, xi, right? So the change in spring energy is calculated by this formula, k x f square minus xi square. So if you want to calculate the spring, let's say in this position, x, is just simply calculated by the formula of a half times k times x squared. So x is spring constant, and x is position square. One thing to be aware that the position here is the distance between the spring current position and its equilibrium point. So just be careful with this. Another thing that I want to point out is the graph. So let's say here the graph is displacement, where you can see position, and here is spring force, which is kx. If you draw a graph, you're gonna look something like this, right? And area under the curve. So area under the curve is equal to half kx times x, which is a half kx squared, which is the spring energy, right? So you can prove this formula by using integral. So work is equal to integral f times dx. So for spring is gonna be equal to kx times dx. So k is a constant, so this is equal to kx times dx, and so this is equal to k, here is k1, so by using the integral rule, it's gonna be equal to a half kx squared. So this is equal to a half kx squared, the spring energy. So we talk about work energy thermal, we know work done is equal to change in kinetic energy. But from this, we can also say change in energy is equal to work done by a force, right? So this, we only know change in work, so work done is equal to change in kinetic energy, but now we can also say change in energy is equal to work done, or work done is equal to change in energy, and the energy include both kinetic energy, spring energy, and gravitational potential energy. So this is just a little bit review session. So spring in series and spring in parallel. So spring in series looks something like this. and K constant, K sum is equal to K1. Oops, sorry. Let me redo this. So this is spring 1, this is spring 2, and K sum is equal to K1 plus K2 plus plus 1 over Kn. And in parallel, K sum is equal to K1 plus K2 plus plus Kn. So this is just a little bit review session. And remember that spring constant measures the stiffness of a spring. So let's do an example. A mass of 8.4 kilogram rests on the top of a vertical spring. This spring compresses 5.2 centimeters. Calculate the spring constant and determine the energy stored in the spring. So we know spring energy is equal to a half kx squared. So from this formula, we know that spring constant is equal to 2 spring potential energy over k, and then take the square root. Over the over the position. So you don't need the square. K is equal to 2 spring potential energy over x4. So the first part asks us to find the spring constant, and part 2 asks us to find the energy stored in the spring. So how do we do this? So this one we know it at rest. So at rest means the net force is equal to 0, right? So this is the spring, this is the object, and the object receives a force of gravity and a spring force. So we know Kx is equal to mg, so K is equal to mg over x. So K is equal to mg over x, which is equal to 8.4 times 9.81 over 5.2 centimeter. So 2 meter is equal to 0.052. So this is equal to wow, this is a very big number. 1584.69 Newton per meter. So this is the spring constant here. So now let's calculate part B, the energy stored in the spring. So we know from part A, we know that K is equal to 1584.69 Newton per meter. And now the spring potential energy is equal to a half times spring constant times the position score, which is equal to a half times 1584.69 times 0.052 meter square, and this is equal to 2.0 3.1425 Newton. Right. So this is not a very large volume compared to a spring constant, but it does make sense because first of all, 5.2 centimeter is not really a large distance, and the spring constant is really very big, so it requires a lot of force and energy to pull the spring. Potential energy is a object precise because of its position in a gravitational field, and and this energy is calculated by using the formula of mgh, where m is mass, g is gravitational acceleration, so 9.81, and h is the vertical position, right? And is this so gravity is a conservative force because gravity does not depend on the path taken, right? So let's do this. Here we have a box at a height of h1 and another box at h2. Right, so what we can say is Fg1 is equal to mg, mg2 is equal to mg, so Fg1 is equal to Fg2, so it does not depend on the path taken, right? So it doesn't matter if the box goes the object here goes this way or this way, right? So this path here does not matter, right? And same thing with gravitational potential energy. Let's say here is the object. It does not matter if it goes this way, but it does matter where the object position is, whether it is at h1 or is at h2. So does this energy, gravitational potential energy, does not depends on the path but its position. So let me do a little bit extension here. Before I said Fg1 is equal to Fg2, but this is not correct because G changes, so right, the volume of G changes. So a more accurate formula to calculate gravity is this formula, G m1 m2 over r squared with a negative sign if you are taking the vector form, because gravity is always a downward force, and we know that force done by gravity, F is equal to Fg over dr. So you can do this integral here, and then you will get a formula of this. Right. So this is a more accurate way to calculate gravitational potential energy, right? So go back to our formula. So we only use this formula. And here G is equal to 9.87. Some people might ask why it does not include a negative sign, because remember, the negative signs represent direction only, and because energy is a scalar quantity, so it does not really care about direction. So since we have talked about potential energy, I'd like to talk more about conservative and non-conservative force. So on the left side, this is the characteristic of conservative force. So the work done by a conservative force is independent of the path taken, like what we previously talked about. And a force is conservative if the work done around any enclosed path is 0. So for example, if this is a object of mass m, and then this is the initial position, right, and it goes up, to HF, and then it comes back again, HI. So this enclosed path, the work done is 0 because the final gravitational potential energy is this. And for the starting point is also mghi, which is equal to its final potential energy. So the work done is 0. And if for non-conservative force, they uses force that are force such as friction or air resistance. So mostly are thermal energy. And this is force take energy away from the system as the energy progress, and you are unable to get this energy back, right? So for example, if you are moving a block on your floor, the block, it has some kinetic friction while it's moving, and this friction, it does work, so it also uses energy. It takes energy away from the system as the blocks move, and you are unable to get the thermal energy back. And for conservative force, they're the opposite of conservative. For non-conservative force, they're the opposite of conservative force, so they are path independent. So it's important to know their path. So let's say we have a box. For a box moving in this path, it has a different energy for box moving in this path, right? So the path matters. So the starting point and the position point also matters. So now we are going to talk about power. So power is the amount of energy transfer or per unit time. So power is represented by the letter P is equal to the amount of work done during a unit of time, which is equal to energy over time. So energy is, work is equal to F times displacement over time. So we know displacement over time is equal to velocity. So power is equal to force times velocity here. And for power, it has a unit of weight. So let's do this. Work has a unit of joule. And power has a unit, T has a unit of second, so this is the unit, so this is equal to watt. So this is the SI base unit, SI unit of power. So we know the unit of joule, right, is equal to kg times meter square over S square, and then S. So this is equal to kg times meter square over S. So this is a unit of power. So let's do a simple example for power. So a 80 kilogram army training does pull up on a horizontal bar. It takes a training 0.8 seconds to raise the body from a lower position to where the chain is above the bar. The training moved for 60 centimeters. How much power do the training muscles apply moving his body from the lower position to where the chain is above the bar? So this question asks to calculate to find power. So let me draw a picture first. So let's assume this is a bar, right? Initially, the training is here, and after 0.8 seconds, the training is here. And let's say this is the chain. And this here, delta y is equal to 16 centimeters. So how do we calculate power? We know power is equal to energy over time. It is also equal to work done over time, which is equal to force times displacement, cosine theta over t. So for this one, is going up. So we need to calculate gravitational potential energy, right? Because as energy moves up, it gains more potential energy. So the force is equal to gravitational potential energy is equal to mgh. So mg is gravity, and h is the total displacement the person moves. Right, so mgh over t. The mass is 80 kilogram. Gravitational acceleration is 9.81 times 60 meters. So 60 centimeters is equal to 0.6 meters. Over the total amount of time is 0.8 seconds, which is equal to 529 watt. So let's do another example here. So an 80 kilogram army trainee does pull up on a horizontal bar. The trainee moves at a speed of 5 centimeters per second, and he moves for 2 seconds. How much energy does the trainee gain? So when the trainee moves up, it gains some potential energy, gravitational potential energy, which is equal to mg times delta h. So the trainee here, it moves out with a velocity of 0.5 centimeter per second. So delta h is the amount of displacement he moves up, and so delta h can be equal to velocity times time. So this equation becomes mg times v times delta t, right? And we know how to calculate this, so we just plug in number and do the unit conversion. So 2 centimeter per second, you need to convert that to meters, right? So we know 100 centimeter is equal to 1 meters, right? So this just cancels off. So 2 over 100, right? Oh, sorry, it's 5 centimeter per second. This is equal to 0.05 times 2. So let's just approximate number. Let's take the volume of 10 here. So 800 times 0.1 is equal to 18 joule. So this is the answer for this problem. So just one thing I want to point out is that you need to be able to change things from one quantity to another here. So let's say we know power is equal to work over time, which is equal to energy over time, so it's equal to force times velocity. But when you are calculating energy, you need to be aware that displacement is equal to average velocity times time. So this formula can become mg velocity times t. And same thing with other problem. Let's say we have a force here and it moves the velocity of d. Although this is not gravitational potential energy, you can still say displacement is equal to velocity times time. Right? So just be aware of this. So we have studied 3 main energy in this lecture, which are kinetic energy, spring potential energy, and gravitational potential energy. Right? And those two energy are potential energy. And those 3 energy are what known as mechanical energy. So mechanical energy is equal to kinetic energy plus potential energy. And by studying the 3 types of energy, we're going to study a very important theory called conservation of energy. So conservation of energy say that the total energy of an isolated system remain constant and is said to be conserved over time. Right. So let's do an example. So let's say here is a spring. right? So initially is at equilibrium point. However, after some time is stretched to a maximum stretch. Right? So let's say here is delta H. So what happened is that we can say the Earth and the spring, they are an isolar system. So the conservation of energy is conserved. So all energy add up should remain same. So remain constant means initial energy is equal to final energy, right? So some people might ask, what about the gravitational potential energy? It changes. So the changes within the system is what known as internal energy. And internal energy include kinetic energy, potential energy, and rotational energy, and so on. So changes within a system is known as internal energy, right? So in this lecture, we only worry about kinetic energy, gravitational potential energy, and spring energy. Let me write this down. So basically, initial energy is equal to energy final energy, right? So EI is equal to EF, so KI plus USI. So spring initial spring potential energy plus initial gravitational potential energy is equal to final kinetic energy plus final spring potential energy plus final gravitational potential energy. So by doing this, another thing you can say is energy gain is equal to energy lost, right? Because the total amount of energy remain constant. So if you gain some energy, you must lose some energy, and the amount of energy you gain must be equal to the amount of energy you lost, so that the total amount of energy remain constant, right? So this is conservation of energy. So let me really even more clear. So you only worry about kinetic energy, spring energy, and gravitational potential energy. So kinetic energy initial, and spring energy, gravitational potential energy. One thing you need to be careful with that. Let's say you are doing a vertical spring, right? And it stretch to some position here. Let's say here is delta H. Then in this system, right, the spring energy, right? The amount of energy the spring stretch, and the amount of gravitational potential energy is gained. Are the two following. However, delta H is equal to delta X, right? So I know in those two equations I use X and H, different letters to represent, but for a vertical spring, this is the equilibrium position, and delta H is the amount of displacement the spring stretch, and it is also the amount of displacement it travels vertically. So for gravitational potential energy and for spring energy, delta X is equal to delta H. So let's think about the spring's maximum stretch. So let's say before the spring looks like this, and after it looks something like this. And let's say this is delta H, right? And we know initial energy must be equal to kinetic energy. So the spring is released. So initially, the kinetic energy is 0. Oops, sorry. And the spring energy. Actually, I'm gonna rewrite this. So this is initially, after, and this is delta H. And initial energy is equal to final energy. So kinetic energy plus spring energy plus gravitational potential energy is equal to final kinetic energy plus spring potential energy plus gravitational potential energy. So let's say the spring is released. Right, so kinetic energy is equal to 0. Spring energy is equal to 0. And gravitational potential energy, so mghi, final kinetic energy. So if the spring has its maximum stretch, so after the maximum stretch it goes upward again, and when the spring has a minimum stretch it goes down. So at the bottom here the spring has a velocity of 0, so kf is also equal to 0, so 0 plus maximum stretch, so k delta h square. So because this is an equilibrium position, here's delta h, so here is delta h plus mghf, right? So now we can say that mghi minus mghf is equal to a half k delta h square. So mghi minus hf is equal to a half k delta h square. So mg delta h is equal to a half k delta h square. So I will just take the absolute value here because I want to calculate delta h. I want the positive volume here. So delta h can be cancelled. So what we can say is 2mg over k is equal to delta h, right? So here is your final answer. So by using conservation of energy, you can know this. So let's do another example of conservation of energy. So this is a block of mass 2.5 kilogram, sliding on a rough horizontal surface. The initial speed of the block is 8.6 meters per second. It is brought to rest after traveling a distance of 60 meters. Determine the magnitude of the frictional force. So F is equal to what? So we know initial energy is equal to final energy, right? So for this problem, I will use two methods to solve it. So initial energy, so we know Ki plus USI plus UGI must be equal to Kf plus US F plus MGF. Okay, so UGF plus thermal energy, right? E thermal. So I know in this slide I only wrote the formula for mechanical energy, but it should be a thermal energy here. It's just often we ignore thermal energy, but here is thermal energy. So because the box slide on the surface, so the gravitational potential energy does not change. So UGF is equal to UGI, and because there is no spring, so USI is also equal to USF. So it just cancels off. So it becomes something like this. Ki is equal to Kf plus E thermal. And because we know the block is brought to rest, so Vf is equal to 0 meters per second. So Kf is equal to 0. So since the final kinetic energy is equal to 0, then Ki is equal to E thermal. So we know the thermal energy in this problem is friction. So energy due to friction or work done due to friction is equal to frictional force plus displacement, right? So this is the equation we need. So let me read this all of the other part. Actually, let me do this here. So we know a half times the mass times initial velocity squared is equal to the following. So friction is equal to mvi squared over 2, and then you move the displacement to the left side, it becomes this equation here, right? So now you just need to plug in the number because we know the mass, we also know the initial speed and the displacement. So F is gonna be equal to, so F is equal to mvi squared over 2d, which is equal to 2.5 times 8.6 squared over 2 times 16. So this is the and then because you want to calculate magnitude, so you should take the absolute volume, but here obviously the volume is greater than 0, so you do not need an absolute sign here. So to calculate the volume, so the final answer is 6.7696 Newton. This is the final answer here. So I will do this problem by using another method here. So we know from conservation of energy, we know that energy gain is equal to energy lost, which is equal to work done, right? So in this problem, initially the block is at a speed of 8.6 and then it goes to rest. So we know it lost kinetic energy. So delta K. And this is due to friction. So energy gain is, it gains frictional energy. So E thermal. So E thermal gotta be equal to delta K, right? And K final is, so final kinetic energy is equal to 0. So work done by friction is equal to F times D. Final kinetic energy is equal to 0. So delta K is just equal to initial kinetic energy, VI squared, and then you can solve for F. So F is equal to mvi squared over 2d. So you just plug in the number again. The speed is this one over 2 times 16. This is also equal to 3.7696 Newton. So two different ways of solving the problem, we got the same result. So another example, a pendulum of length 1 meter is released with a string at an angle of 10 degrees to the vertical. Find the speed and the mass of the pendulum when it passes the lowest position. So here is a pendulum, its lower position. So let's say here is maximum, not maximum, I mean. And here is 10 degrees, right? So here 1.0 meters. Here is also 1.0 meters. So you can use conservation of energy. So you need to know here. Here is gonna be delta H. So how do we find this? Well, I know the picture here is not drawn to scale, so let's redraw the picture. Here is 1 meters, right? So here is also 1 meters. And we want to know here, the angle here is 10, right? So you can know this here is gonna be equal to 1 cosine times 10 degree. So here is gonna be equal to 1 minus 1 cosine 10 degree, right? So this is gonna be equal to delta H. Yeah, so let me erase this and write here. Delta H is gonna be equal to 1 minus 1 cosine 10 degree, which is equal to 1 times 1 minus cosine 10 degrees. Right. And so let me draw a small pendulum here. Here is delta H. So you can also find the speed of the mass by using conservation of energy. So let's say here is initial energy is equal to final energy, right? And initial energy here. So from here to here, you can also use two methods to do it. You can use initial energy is equal to final energy, or you can use the amount of energy gain is equal to the amount of energy lost. So from here, so same thing, I will use two methods to solve the problem. So Ki plus Usi plus Ugi is equal to Kf plus Usf plus Ugi. Here should be plus E thermal, but you do not need to worry about thermal energy in this problem because it does not mention it. It will be a little bit complicated if you include thermal energy. So initially, let's say this is the initial energy here. So here, we know it does not have spring energy at all. So final spring potential energy is equal to initial spring potential energy is equal to 0 joule. And for here, here's delta H, and here is delta H, and here is Kf and Ki. So what I'm gonna do is I'm gonna do this. Ugi minus Ugf is equal to Kf minus Ki, right? So delta Ug is equal to delta K, right? And we know K initial. Let's say this is the initial. Initially, it must have a velocity of 0 meter per second, because it's released. Release means the initial speed is equal to 0. So delta K is just equal to Kf, and for changing gravitational potential energy is mg delta H is equal to a half m times vi squared. So m cancels out. Oops, sorry, here should be m cancels out. So g delta H is equal to a half vs squared. So 2gh, and then you take the square root is equal to vi, which is equal to, let's just approximate, delta H 1 minus 1. So this is equal to vi, so vi is equal to 0.55 meter per second. Right, so this is the first method you can use to solve the problem. The second method is to use energy gain is energy loss. So you can go directly to the step, because the amount of gravitational potential energy it lost here is equal to the amount of kinetic energy it gains here, right? Or changing gravitational potential energy is equal to changing kinetic energy, right? So in the second method, you can just directly go to this step, and then you'll have the same answer here. So this is the end of this video. Follow my website and subscribe my channel if you like this video. Post your suggestion down in the comment, and I will post a link to this PowerPoint in the description part. So thank you for watching the video.